All right. Okay, good to see everybody. This is the last week of the 6 weeks. So Friday, I'm going to be finalizing all the grades. So I've got a couple things up here on the board. First, the focus activities, and you have your last one right here. This is number 6. You're only going to be turning in numbers 4, 5, and 6 because you've already previously turned in numbers 1, 2, and 3. They are going to be due tomorrow is when I'll officially be looking for those. But if you want to turn them in before you leave today and just be done with them, absolutely fine. We'll just take care of that at the end. I'm going to go ahead and stop a little early so that I can pass back your tests and let you see how you guys did. Sir?
What's the day?
Today's the 11th, Monday the 11th.
It's my sister's birthday.
Oh, really?
Yeah.
Well, wish her a happy birthday. How old is she?
She's 20.
20? Wow.
Yeah.
Okay. She here in town?
No.
Oh,
She's
well,
in New Jersey.
New Jersey.
Yeah.
Okay.
There.
Nice. Well, your class average on Thursday of last week, we already kind of talked about it, but 83.4, so you guys did a really good job. But if anybody's grade was below a 70, you still have time to retake. In fact, all those deadlines, if there's any outstanding papers that still need to be turned in, retakes, anything of that nature, all of that we need to have done by Thursday morning at the end of tutorials, please. So I'm here every day. If you have a question, please let me know. I'll do whatever I can to help you out. And we're going to go ahead and start our next lesson today. We're going to look at sum and difference identities. But before we get there, here is the last focus activity for the fourth 6 weeks. It says, if a rocket is launched from ground level, the maximum height that it reaches is given by this formula. H equals v squared times sine squared of theta over 2g, where theta is the angle between the ground and the initial path. So it's this measure right here. So pretend this was the positive x-axis. Okay. The initial path of the rocket. V is the rocket's initial speed, so how fast the rocket is moving, and g is the acceleration due to gravity. So 9.8 meters per second squared. That's the pull of gravity. So for those of you who have been in physics or are in physics, you'll recognize that value. So A says to verify that v squared times sine squared of theta over 2g equals v squared tangent squared of theta over 2g secant squared of theta. So this is exactly what we've been doing last week. We're using the identities just to show that it does equal the formula we were provided. I would probably definitely go ahead and start with the right side just because it has more going on. But how can I rewrite this to end up with v squared sine squared over 2g? What would you do, Brandon?
On the top, I would change everything to sine and cosine.
Okay, so he says change to sine and cosine. So v squared remains the same. So now tangent squared would be, bless you, sine squared of theta over cosine squared of theta over. Okay, so secant is 1 over cosine. Now, if I were to write that out, that'd be 2g times 1 over cosine squared of theta. So I could go ahead and multiply those and just have one fraction. So 2g over the cosine squared of theta. And I could actually even do the same thing here, multiplying that fraction by v squared. V squared would be up in the numerator. Okay, so now I've got one fraction divided by another. And how do we simplify these? The reciprocal, that's right. We multiply by the reciprocal of the denominator. So up top, we're going to have v squared sine squared theta over cosine squared of theta times, now we're going to go ahead and flip this bottom fraction, cosine squared of theta over 2g, and what happens? Cosines are going to cancel. Yes. All right. And what we are left with is v squared sine squared of theta over 2g, which is exactly what we wanted to show. Now, what do we do at the end of these? QED. There we go. Quite enough done. That is exactly right. Perfect. Because remember, you know what the last step is going to be. So these types of problems, it's not like they have a specific answer. It's the path you choose. It's how you get there that really is the answer. And there's a lot of different ways that you can do besides this one. Okay. So good. B, suppose a second rocket is fired at an angle of 80 degrees from the ground. Okay, so what we're going to do here is just go ahead and start to plug in. So they're giving me 80 degrees. What would that represent? That's theta. Okay, that's my measure. Now from the ground with an initial speed of 110 meters per second. So what's that? Is that V or is that G? That's our velocity. There we go. That's how fast it's moving. So that's my velocity. And then find the maximum height of the rocket. So we have everything we need. We just need to go ahead and substitute everything in and see what the result is going to be. So let me move this right here. Okay, so the formula says that the height is going to be found by the initial speed squared times sine squared of the angle made with the ground divided by 2g, which is the acceleration due to gravity. Okay, so v squared, well, that's just 110 squared times sine squared of 80 degrees divided by 2 times g, and what was g again? 9.8. So 2 times 9.8. I would probably wait until the last step to round because that would affect the answer. That's a good idea though. Does your science teachers or your physics teachers have you round that prior to? Some of them do? Okay. All right, well, let's see what we're going to get. So I'm going to say parentheses 110 squared. Now for sine squared, I'm going to go ahead and put in sine of 80. You'll notice I'm in degrees. Okay, so that's exactly what we want. So I'm going to hit sine of 80, but then I'm going to go out and square that. So that's equivalent to sine squared of 80. Is everybody okay with that? Divided by, we wanted to double the acceleration due to gravity, 9.8. Okay. So what should I be getting as soon as I push enter? I heard 500 and what? 598.7. That's exactly right. Okay, good. Who else got that? Anybody else get that back? A few folks? Okay. So 598.7, and we're talking in meters. Okay. 598.7 meters. Perfect. Just working with an equation. Okay. How we doing? Okay. All right. Good, good, good. So I'm going to take this right here. All these extra copies. Remember, the focus activities are due when? Due tomorrow. So if you have lost or misplaced one, there should, there's the key word, there should still be those extra copies for numbers 4 and 5 in there as well. Okay. And if you want to turn those in today, perfectly fine. Otherwise, I'll be looking for those tomorrow. Okay. So here's our next lesson. Oh, yeah, we'll turn them in at the end. Yeah, we'll turn them in. Thanks. Okay, so here's what we're going to go ahead and talk about. There's a couple of other identities that I want to go ahead and show you. We've been dealing primarily with the reciprocal. We've had the Pythagorean identities. We've had the cofunction. We've had the even odd. Now the even odd and the cofunction, they're going to be playing slightly bigger role in these next few lessons, but really it's the same idea. We're just adding on a few extra identities. These are what we call the sum and difference identities for our trig functions. So we're going to be looking specifically for sine, cosine, and tangent. Okay, and you could go ahead and take, say for example, the other three like cosecant. You could just take the reciprocal of what you have here, and that would work out just fine. That's why we don't have to really list those. But here's the thing. If you have sine of two items, so alpha and beta here, you always go in order. Alpha is always first, beta is always second. Okay, and these can represent degree measures or they can represent radian measures. Okay, whatever they represent. If you have the sine of two measures that you're adding, well, this is the formula that you would use. It's sine alpha cosine beta plus cosine alpha sine beta. So what I like to say is that in the products, sine alternates. So you'll notice in the multiplication parts, it's sine times cosine. You're using two different trig functions. And you'll also notice if it's a positive, what happens? What are you still doing in the formula? Okay, you're still adding, right? Now look at the difference for sine. If I'm taking the sine of two items that I'm subtracting, again, doesn't matter if they're degrees, doesn't matter if they're radians, okay? The products are still going to be the same. Sine alpha cosine beta minus cosine alpha sine beta. It's still sine times cosine. Alpha and beta are still in order from left to right. And you'll notice if it starts with a minus, you do what? You still subtract. Sine keeps the same sign. Okay. Now, with those characteristics in mind, let's look at cosine, whether he's a sum or a difference. Now, while sine likes to alternate, see it's sine times cosine. What does cosine want to do? Yeah, cosine doesn't want to alternate. He wants to multiply cosine times cosine, sine times sine. Okay, and you'll notice the pattern. Cosine alpha, cosine beta, sine alpha, sine beta. Same thing if it's a difference. Cosine alpha, cosine beta, sine alpha, sine beta. But there is another difference. Okay, if you start with a sum and cosine, what do you do in the formula? Subtract. Cosine always wants to change the operation. Okay, sine keeps the same sign, but cosine does not. Okay, so here when I have cosine of alpha minus beta, that would be plus. So minus would change to a plus. Okay. Is everybody okay with the patterns? And the more we work with these, it's going to be easier for you to expand and condense these. Okay. Does anybody want me to give you just an example right off to kind of help solidify this a little bit? You do want me to? Okay. So let's say we have, let's say sine, and let's say that alpha is equal to 20 degrees, and let's say that beta is equal to, let's say 30 degrees. Okay, so I'm going to take sine of 20 plus 30. Okay, so knowing those two values, well, let's just go ahead and apply them to the formula. Okay, so because it's sine of addition, I'm going to use this formula right here. But we always go in order. Remember, this is alpha, and that's my beta. So the first part right here, sine of alpha cosine beta, well, I'm going to say sine of 20 times the cosine. Whoop, if I could write today, that'd be fine. Cosine of 30. And what does sine like to do? Sine always keeps the same sign. So we started with a plus. I'm going to put a plus, and now I'm going to fill in this. Cosine alpha, sine beta. So this would be cosine 20 times the sine of 30.
So how are we know if we're using like the cosine and sine? Okay, so if we're using sine,
Oh, so how we know if we're going to be using an adding or subtracting?
no. So is it like, so if there's sine, alpha and beta,
Mm-hmm.
alpha plus beta equals, that means we're using the top one, and if it's cosine, like alpha plus or alpha plus beta.
Oh, yeah, you're just going to find the pattern that it fits to.
So like
Yes. Yes.
okay.
Okay. Yeah, so it's just a formula that you're going to plug in, very similar to what we were doing on the focus activity. Okay. Now, if I were to give you something like, let's say cosine, and let's do a difference. Let's say 70 minus 30. Okay. So that this first one is always alpha. The second one is always what? Beta. Well, since I have cosine of a difference, I want to make sure to use this formula. But remember, the products don't alternate, and what do we change? There you go. So we want cosine alpha, cosine beta. So this would be cosine 70, cosine 30. Since I started with a minus, I go plus, and now I want the second part of the formula. Sine alpha, sine beta. So that would be sine of 70, sine of 30. Okay. Is everybody okay with that? Okay. Now, why do we have these extra identities? I mean, why do we have these formulas that we want to go ahead and take the time to look at? Well, I'm glad you asked that question. Okay. What if I were to give you something like this? Let's say the sine of, let's say 75 degrees. Okay. But we don't have a calculator, and I want to evaluate that. Okay. So see, the idea is the angle that I'm given, is that something that we recognize on the unit circle? 75? Now remember we have 30, 45, 60, we got 90, we've got basically those 16 points, right? Okay, so the idea using these identities, well, why don't we use measures that we are familiar with on the unit circle to rewrite this? So for example, to get 75, couldn't I say that sine of 45 plus 30? Yeah. And see, our 30 and 45 measures that we know on the unit circle. Yeah. Okay. So this would be my alpha, this would be my beta. So I could go ahead and expand that, and I can evaluate that. That's the goal. Okay. Is everybody okay with that? So let's go ahead and practice this. And really, does it matter if I did 30 plus 45? Would that still give me 75? Yeah. But however you write it, that first one is always going to be considered alpha. Okay. So because I have the sine function, I want to make sure to alternate when I multiply. So sine alpha, cosine beta. So I'm going to say sine of what? Sine of 45, cosine of 30, plus or minus? Plus, sine always keeps the same sign. Plus, now I want cosine alpha, sine beta. So that would be cosine 45, sine 30. And then we could evaluate those pretty easily using our triangles again. Does that make sense? So we're kind of expanding our knowledge of the unit circle. Now, there's only so many extra combinations we're going to be able to get adding or subtracting those 16 values on the unit circle, but at least it gives us a little more room to work with. Okay. And then we also have those for tangent. Now, you'll notice, I want to go ahead and show you very quickly, tangent of alpha plus beta, tangent of alpha minus beta, the form itself is always going to be the same. You'll notice up top in the numerator, you've got a tangent alpha, tangent beta. That is exactly what you have over here when you're subtracting. Tangent alpha, tangent beta. Down in the denominator, you have a 1 tangent alpha times tangent beta. Over here, 1 tangent alpha, tangent beta. But what's the difference between the sum and the difference for tangent? It's the signs. And you know how I choose to remember these is whatever sign you start with, if you start with a tangent of a sum, you keep that operation up top, and it's the denominator that changes the sign. Because if I go ahead and apply that idea to the other one, see, I'm starting with a minus, so I keep the minus up top, but it's down below that I change it. Okay. Is everybody okay with that? And let me give you just another example. Okay. Like let's say I were looking for, tangent of 15 degrees. Now I want you to help me out with this one. Using the measurements that we have on the unit circle, like 30, 45, 60, and so on, how can I add or subtract those to get 15? You could do 45 minus 30. There you go. And it doesn't have to be those two. Could I take 60 minus 45? Yeah. Any values, as long as they will give you what we want, is exactly what we're looking for. So let's say this is tangent of 45 minus 30. Now, because of the way I wrote it, the first one is always what? Alpha. The second one is always beta. Okay. So let me go ahead and just plug it in. In the numerator, you've always got tangent alpha and tangent beta. So I'm going to say tangent of 45, tangent of 30. Would this be a plus or a minus there? Why? There you go. The numerator always keeps the sign that you're using. We were subtracting, so I'm going to put a subtraction right there. So that means what has to go in the denominator? It's got to be a plus. Now it's 1 plus, but it's always a product of the two. So tangent alpha would be tangent of 45 times the tangent of what? 30. Just think of these as a formula, just like we did on our focus activity. You just plug in the values and then you simplify. Is everybody okay with that? Okay. Now this one here, it asks you the question, what patterns do you see that could help you memorize these formulas? Well, I just wrote down, what I like to do. Sine keeps the operation when expanded. Cosine changes the signs. Okay, sine alternates sine and cosine, but cosine is grouped cosine, cosine. So basically what we were just talking about. Okay. All right. So we just have 6 new identities along with the others that we've been working with. Is everybody okay with that? Okay. Well, let's do some problems here. Now, for IS, I went through and I went ahead and proved these rules to those folks. This is actually the proof of the first one. It's probably one of the longest proofs we've done by now. I'm not going to hold you responsible to that, but if anybody is interested, if anybody would like to see it at some point, just let me know and I can run through that pretty easily. You do want to? Oh, okay, because Brandon was over there raising his hand. I probably won't do it today, but maybe sometime later in the week. Okay. It'll probably take us about 15, 20 minutes if we were to actually do it. Okay. I am not going to hold you responsible for that. Okay. If you just know, take my word that these rules work, you're good to go. Okay. All right. Actually, I could. I could print that off for you if you want. Yeah, okay. Remind me at the end and I'll get that to you. Okay, now before we go ahead and get started, I want to go ahead and remind you about some triangles because we're going to be, dealing with some triangles again in order to help us out. So there are 2 types of triangles that I'm dealing with. Okay, and they're special triangles. So what's one of them? We have 30, 60, 90. So let's say this one is the 30, the 60, the 90. Okay, and the other one's a what? It's a 45, 45, 90. Okay. 45, 45, 90. So this is going to go back to what we were doing when we were evaluating the trig functions. Okay, in order to simplify the formulas, we have to do that. So remember, we're on the unit circle, right? So whether you have the first or the second triangle, what's the hypotenuse of each? Oh, no, we're getting there. Okay, but what's the length of the radius? Remember, that's the radius for the unit circle. It's 1. So we're on the unit circle, so the radius or the hypotenuse for each has to be 1. Okay. Now, does anybody remember what the ratio lengths are going to be for those sides? Square root of 2 is a part of it. X square root of 2? Or we could work backwards if you wanted to. We know that, let's use the relationship. We know that the lengths are always x, and that the hypotenuse is x square root of 2. Well, since I know that this length is 1, I'm going to set him equal to the side length we should have. So I'm going to say 1 equals x square root of 2. Oh, close. Well, how would I solve this for x? Oh. Well, let's see. How would I undo the multiplication? I would divide, right? Now, those square root of 2's would cancel. There's my x. So 1 over the square root of 2. But we don't like those expressions where the radical's below, right? What do we call that where we remove it? We rationalize. So I've got to multiply by the square root of 2. Square root of 2. There you go. So these 2 lengths right here, x, have got to be the square root of 2 over 2, square root of 2 over 2. And it's been a while since we've seen those, but do you guys remember that? Okay. Now we can do the same thing over in a 30, 60, 90. But let's see if anybody remembers. There's 2 fractional lengths. Does anybody remember what's always across from 30? You're on the right track, but that's for the other leg. Okay. Yeah, now the relationship is whatever's across from 30, that's your shorter leg. The longer leg is the shorter times the square root of 3, and the hypotenuse is always double the shorter leg. Oh, not 2. Because 1 is double what number? 1/2. Now, hey, you're fine. Okay. And let's do the same thing we did a moment ago. I know that this hypotenuse is length 1, but I also know it's represented by 2x. And how would I solve for x? Divide by 2. So see, that's where we get the 1/2. Now, to get the longer leg, I take the shorter leg and multiply by the square root of 3. So 1/2 times the square root of 3, well, what's that? And let's put it over 1 to make it a little easier. Square root of 3 over 2. There we go. And this is where you simplify the formulas. We already saw how we expanded them. So like, let's take this first one. Okay. Let's say I want tangent of 45 degrees. Or remember, what's tangent's ratio? It's always what over what? And you can do it in the side lengths if you want to. What starts with an O? The opposite over, what's the A? The adjacent. So opposite over adjacent. Or you can go ahead and say y over x, right? So let's say we're dealing with this 45 degrees. Well, the y value is the square root of 2 over 2 divided by, what's the x value? Square root of 2 over 2. Well, what's anything divided by itself? 1. So what we were doing previously is how we're going to simplify these new formulas. What if I wanted cosine of 60 degrees? Okay, so I'm looking at this angle right here. Remember, cosine, what's his ratio? It's always x over r. Okay, well, what's the x value in this triangle? It's 1/2 divided by r, the radius. Well, what's 1/2 divided by 1? 1/2. You guys remember doing that? Creating the triangle and then finding the ratio? Okay. That's what we're going to be doing here. We're just going to be combining it all. Any questions? Okay. All right. Well, let's practice this. Let's put it into practice. Okay. Let's go back up here now. Example 1. It says find the exact value of cosine of 70, cosine of 40, plus sine of 70, sine of 40. Now, all of these rules are reversible. I can expand them, but I can also take an expansion and I can bring it back down to just a single trig function. Okay. What would you think this guy is right here? Is he a cosine or a sine function? Okay. Why would you say cosine over sine? There you go. What are you noticing when he multiplies? The cosines are together and the sines are together, right? Only cosine does that. So I know this is a cosine. What do you think alpha is? Yeah, because it always is written in order. The first value is alpha, so 40 should be beta. So I'm going to say 70, 40. Well, now, wait a minute. Brandon just said minus. It says plus. When you expand cosine, you take the opposite sign. So if I pull it back, that should be minus. So see, here's the thing. 70 and 40, are those values that I can simplify on my unit circle with a triangle? Because they don't create special right triangles, right? But see, now condensing it, what's 70 minus 40? Cosine of 30. And is that a triangle that I can simplify? Yes. In fact, let's go ahead and do it. You'll notice I've got the grid here. What quadrant would 30 degrees be in? The first one. So I'm going to go ahead and draw a terminal side right there. So this is 30 degrees. I always connect it to my x-axis. So that means this one's 60. Now think about the triangle that we just reviewed. Okay? Because we're on the unit circle, the radius, the hypotenuse, is always 1. What's always going to be across from 30? Oh, 1/2. Now the relationship would tell me x. What's always across from 60? Square root of 3 over 2. Okay. So now what was cosine's ratio again? It's x over r. So what's the x value here? Now remember, the x is always horizontal. The y is always the vertical. So it'd be square root of 3 over 2 divided by, what's the radius? 1. So what's the square root of 3 over 2 divided by 1? There you go. So this one we just work backwards, but a lot of times you're going to expand it to use values that you're comfortable with so that you can get your final answer. Okay. Let's go ahead and try one more, and then we'll go ahead and call it quits for today. Now this one, we are not finding the answer like we did on number 1. You're not finding me a ratio. All I want you to do here for A is condense this down to a single trig function of what measure. So it's got to be sine or cosine, but don't say it out loud. Give everybody the opportunity. So it's either got to be sine or cosine. If you decide it's a sine function, then you're going to keep that plus. If you decide it's a cosine, then you're going to make that plus a minus, because remember, cosine always changes the operation. Okay. Now, how am I going to figure out which one it is? Is it a sine or cosine? Sine? But wait a minute, the other one was a cosine. What makes this one a sine?
They like take sine and cosine, like the pair together instead of just sine.
There you go. Look at the products. Are you multiplying the same trig functions or different? Different. Sine does that. Cosine wants to multiply the same trig functions. So this can't be cosine. It's got to be sine. Well, what's alpha? That would have to be 22 because that's the very first value. What would beta be? 13. So this is actually sine of what? 35. That's it. Now, because 35 is not one of the measures off my unit circle, we're not going to worry about evaluating that. We're just going to leave them as is. Is everybody kind of starting to get the idea? Okay. Like I said, this is just the first day. We're going to spend several days on this. Now, unfortunately, we're not going to be able to do this tomorrow. The administration has asked that we take Tuesday the 12th, the whole entire class period, to perform a writing assignment. So I'm going to have a little paper I'm going to have you guys do when you come in tomorrow. It's nothing huge. I know it's in math, writing. We write in proofs, but typically the way we do math, we don't really write. But to make, a little more incentive, I'm going to record it as a test grade. So if any of your grades is a little low, this right here should be, along with the focus activities, another basically guaranteed grade for the end of the 6 weeks. Okay. So I'll talk to you about the instructions tomorrow, the prompts, and then on Wednesday, we'll get back to this. Okay, so just kind of letting you know. All right. Let me go ahead and pass back your paper.